Okay, so right now I want to walk through the MCMC sampler code. I'm going to start off at the title, Build the MCMC sampling. So I'm assuming you've ran everything prior to this line of code, and so we'll just dive right into it. So we first want to set our seed so that we can reproduce the results in running this MCMC. We want to set the number of iterations that our MCMC will run for. So in this case, I've specified it for 20,000 iterations. And now here, this is an aspect of the MCMC that I did not discuss in the PowerPoint, but is a very important part of the sampling. So here, I'm specifying the tuning parameters. These will function as the standard deviations for our Gaussian random walks that will be used to generate proposals or candidate values for our parameter estimates. You'll notice that I have two different tuning parameters. There's just tuning. This will be used for the intercept and sigma, and then tuning underscore B1. So this will be used for the Gaussian random walk to generate proposals for the slope effect. And this was just something that I needed to adjust, and you'll see why later in the code of when we calculate acceptance rates. Okay. Next, we want to just build an empty data frame. So I'm going to call that our posterior. We're going to specify the number of iterations. So this is a data frame with 20,000 rows because iteration goes from 1 through n iterations, so 20,000. Then we're going to create some empty columns for our posterior samples of the intercept, slope, and our sigma. Similarly, I'm going to create 3 additional columns. These are going to track whether we accept or reject our candidates on each iteration. Something to note is that by specifying these as numeric n iterations, that's just a vector of length n iterations. So in this case, 20,000. And the default value will be 0 for these 3 variables as well as these 3. Note, iteration goes from 1 to 20,000. Okay. So remember step 0. So step 0 is choose an initial value for the MCMC sampler. So we're going to do this for each of our parameter values. So for our intercept, this is B0 or B0. We're just going to generate a random number from a uniform distribution. So this is how you do that. This just means random number, uniform distribution. We just want one number somewhere between -10 and 10. And we're going to do this for each of the parameter values, but you'll notice that for sigma, I obviously don't specify a negative number as plausible because standard deviations can only be positive. Now, these can be just about any value. These are, again, just starting values. This is just something to get the MCMC started. Now, above, I have a calculate likelihood function. And so I'm not going to go through the specific steps of the calculate likelihood function because you should have already seen that already. But here I'm just passing my data. So this is the Y, so the log elasticity data, the year, so our variable of interest, and then the first initial value for our intercept, our initial value for our slope, and then finally for the sigma. And this is just calculating the likelihood for these initial values. Next, we actually want to run through the MCMC, and we're going to do this with a for loop. Now you'll notice here, I have 4 commented out. So this is what it will look like for your code, and this I equals 2 will actually not be there. But to illustrate things step by step, I want to set I equal to 2 so that I can show you what each step of these looks like. So let's go back and run everything thus far. And then if we want, we can see that our log likelihood for the initial values is negative 3,236. And this is not so much of an important number, but remember that this is our log likelihood of the data given the parameter values for the initial parameter values, that is. Okay. And so we're going to start with I equals 2 because we've already generated initial values. We've essentially already run the first iteration. So we're going to begin at iteration 2. Okay. So we're going to begin with updating our intercept. So this is update B0. And remember our steps for the MCMC. So our first step is to propose a candidate value. And we're going to do this with a Gaussian random walk. This is a pretty simple process. We're just going to use the rnorm function. We're going to generate one number with a mean that is the value or set to the value of the last drawn parameter estimate. And this is one of the reasons why we start with I equals 2, that is the iteration 2 of the MCMC, because here, now the mean is going to be set to that initial parameter value. The standard deviation for this Gaussian random walk will be our tuning parameter. If we do this, we have our candidate value. And so our candidate value is negative 5.39 for the intercept. And now we need to calculate or estimate our probability of accepting the candidate value. Now this involves first calculating the likelihood of the candidate. And now for this, we're going to use the same function as before. So the calculate likelihood function, we're going to give it the data just as we did before, the x variable, so in this case, year. And then for the intercept, we're actually going to use that candidate value. That's what we're going to pass to the calculate likelihood function. And if you'll remember, whenever we estimate multiple parameters, we're going to do so one at a time, and we're going to hold the other parameter values constant. So you'll notice here that our slope and sigma parameters are going to be held to the same values or the same previous last drawn values in that posterior distribution. Next, we're going to calculate our joint distribution for the last drawn parameter estimate. So I'm calling that joint current right here. And remember, we're working on log space. So I've already calculated the likelihood, and then now we just need to use our prior B naught function to calculate the prior for our intercept. I'm going to run that. And then we need to do the same for our candidate likelihood. Oh, and I should say, because we're on log space, we're adding these, not multiplying these. Remember. Okay. So, I didn't run candidate likelihood. There we go. Okay. So now we have our joint distribution. So we just essentially used Bayes' rule to calculate the probability of our initial parameter value. So negative 5.444 and our candidate value. Okay. So now we need to calculate the ratio of these probabilities. Now, mathematically, I displayed this as the joint distribution of the candidate divided by the joint probability of the candidate divided by the joint probability of the last drawn parameter estimate, which is joint current here. But again, we're working on log space, so I'm going to subtract them. However, I do want these back in a probability space because next we're actually going to use these as probabilities. And so to get them back on our probability space, we're going to exponentiate them. And that's why we have this here. And then I'm going to set that equal to R. And this is going to be our ratio of probabilities between the candidate and the current parameter estimate. And now step 3, we need to accept or reject our candidate value. And remember, we use R to do this. Now, the code for this is going to be a little bit confusing in terms of how we implement it. So I'm going to cut really quick to a different line of code to illustrate what we're actually doing. And then I'm going to go and show the short form of the code for our decision rule to accept or reject the candidate. Okay. So here, what we're going to be doing is we're going to be specifying our decision rule for accepting or rejecting the candidate value for our parameter estimate. So remember, our decision rule is if the ratio of the probability between the candidate and the last drawn parameter estimate is greater than or equal to 1, then we're going to automatically accept the candidate. If it's not, then we're going to accept the candidate with a probability of that ratio. And so one way we could implement this is we could say, okay, if R is greater than or equal to 1, then our decision is to accept. This is very straightforward. This is exactly what this decision rule specifies. Else, so if R is less than 1, then we need to accept the candidate with probability R. And so this line of code can do that. So we have our decision variable, so it can either be accept or reject. And we're going to sample a vector. That vector has either accept or reject in. And this is the outcome of what we want to decide. So this works out. We're only going to draw one of these. So we're either only going to accept the candidate or we're going to reject it. And we're going to accept it with R probability and reject it with 1 minus R probability. And this latter aspect captures this accept the candidate with the probability of R. Based off of the outcome of this set of code, we can make our decision. So if our decision is to accept the candidate, what we're going to do is we are going to store that candidate into the posterior distribution. So the candidate value is going to go into the ith row of the intercept column. We're also going to indicate that this candidate was accepted. So accept underscore B0 equals 1. Oh, this should be an I. And we're actually going to update our likelihood, and the likelihood is now going to be the candidate likelihood. Now, if we do not accept the candidate value, we get into this else region. So if we reject the candidate, what we're going to do is we're going to keep that last drawn value for the posterior distribution. So it's just going to stay the same essentially. Now here we do not need to put posterior except B0 I equals 0. That is that the value was rejected because that column is already filled with zeros. In addition, we do not need to update the likelihood because it's just going to stay the same. In other words, everything's going to stay the same. When we reject the candidate, we're just going to store the last drawn parameter estimate in the posterior. Now, this line of code works perfectly fine. It will give us our answer, our parameter estimates. However, we can actually do all of this in a much more concise way, and this is the more commonly used set of code. And this is where the quote-unquote short form of my code comes into play. So the way this is going to work is that we are going to draw a random number from a single random number from a uniform distribution. And that uniform distribution by default with the runIf or runIf function ranges from 0 to 1. And if our ratio of the joint probability of the candidate versus the last drawn parameter estimate is greater than this randomly drawn number, then we're going to accept the candidate. What I want to get across is that this is functionally equivalent to what we did above. It just does it in a much more concise and quicker way. You can test this out if you would like, but all this to say is that it's functionally equivalent. And then again, if we do not accept our candidate up here, then we're going to reject it, and we're going to use the same line of code that we did before. All we're going to do is we're going to save that previously drawn posterior estimate. Okay. So I'm going to go back to the MCMC sampler, and we're going to use the line of code that I had before, or this short form code for step 3. Okay. Okay. So let's get back to the MCMC sampler. So we just decided whether or not to accept or reject our candidate value. Oh, I didn't calculate R. So this is the ratio between our the candidate on iteration 2, or the joint probability of the candidate on iteration 2 versus the joint probability for our initial parameter estimate. So remember, it's just these two values. And again, I'm just working with iteration 1 versus iteration 2. We'll go with our accept or reject. So you'll notice that R here is much higher than 1. So this is automatically going to be accepted. So here we store our posterior. Let's check out what that value is. So this is what our candidate was. Because again, R was much greater than 1, so we accepted our candidate. You'll notice that the code for this illustrates that it was accepted, and then we also save our likelihood here. Now, we're going to estimate or generate a candidate for the slope coefficient. So now we're going to update B1. And it's going to be the exact same process. So we're going to generate a candidate using a Gaussian random walk. So we'll generate our candidate. Remember that I'm using a different tuning parameter because the slope was a little bit funky when estimating originally. We're going to calculate our candidate likelihood. for that value that we just proposed. Going to calculate our joint likelihood, not joint likelihood, our joint distribution, joint probabilities, I should say, for the current and the candidate value. We're going to calculate our acceptance probability, and then we're going to make our decision. Exact same process that we went through with the intercept. So now we are going to proceed and update our sigma parameter estimate. This is going to be slightly different than how we updated the intercept and slope. So we are going to propose a candidate just like we did before, and we're going to do this with a normal distribution. Now you'll notice that I also have another set of code commented out here. This is actually another way that I was taught to propose candidate values for the sigma parameter. Here, I just still use the Gaussian random walk because it'll still work for our purposes. Now, where things deviate is that remember that a standard deviation cannot be below 0. And so it is theoretically possible that when we generate a random number from a normal distribution, that we will get a negative value. And so this gives us a little bit of an issue. And so what we're going to do is we are going to insert another decision rule, essentially. So if the candidate value is less than 0, so essentially if it's outside of the range that we wanted to use, then we're going to automatically use the previously drawn parameter estimate for sigma as this for this iteration of the posterior sigma. If we have a candidate value that is greater than 0, so it is a plausible value for a standard deviation, then we're going to go through the sampler just like we did for the other parameters. So again, we're going to calculate our candidate likelihood, our joint current probability, our probability for the candidate of the parameter estimate, calculate our acceptance probability, and then finally decide whether or not to accept or reject this parameter value. You'll notice that this very last brace is commented out. That's because, again, I commented out the for part of this code. When you look at this code, those will not be commented out. This was just to illustrate the individual steps for the code. But keep in mind that after we get to this point of the MCMC, it's going to go back to the beginning of that for loop, and we're going to begin again with the intercept value. We're going to generate or propose a candidate value for the intercept using a Gaussian random walk, and then we're going to go through the steps of that MCMC sampling. All right. Hope this was helpful.